Saxon Algebra 2, Lesson 29. Oh my gosh, students, you know I love a good dirt problem. Distance equals rate times time. We've reviewed type 1, that's Lord of the Rings, where the distance going and the distance coming is the same, right? There's Frodo and Sam going together to Mount Doom. Or maybe it's Frodo and Sam and Gollum chasing them. I don't know. Oh, there's cat hair on my book. That's not okay. Or it can be Frodo and Sam going to Mordor and then returning to the Shire, right? But in both of these cases, the first distance is equal to the second distance. And so when we substitute in rates and times, we get rate 1 times time 1 equals rate 2 times time 2. And this is what we can use for the base equation, right? And then the book gives us all kinds of information that we can plug in. This is the first kind. This is Lord of the Rings style. All right? Today we're reviewing type 2, which is Titanic style. Ship leaves England, iceberg leaves North Pole, they bang in the North Atlantic. It's a sad story, right? Or, if you want to be even sadder, here's Jack and Rose clinging to the piece of debris in the icy cold ocean after the crash. And poor Jack, you know, he goes one way. He goes down to the bottom of the ocean, but we're going to just flatten it out. And here's Rose returning back to, she goes to New York, doesn't she? I think she's an American. But in any way, they go their separate ways after floating on the debris. So this is Titanic style, and that's the kind we're reviewing today. Titanic, all right? So in these, our two distances are not necessarily equal to each other, but they do add up to a total distance that we call K. All right, so in these we say that the first distance plus the second distance equals some sort of combined total amount. And then we can substitute in our rate times time, because we know that distance equals rate times time. So we can change that. And this is the more workable base equation. This is the kind we're reviewing today, but of course, the trick is when you read the story and the problems, most of the time, I mean, in the practice, you'll know that it's this type. But when you run into these in the homework, the first thing you have to do is figure out, what have I got here? Is it Lord of the Rings style or is it Titanic style? And of course, we're going to get a third kind here before too much longer. So that's really the hard part of these problems, is that you can pretty quickly identify it's a dirt problem. And that's why it's so important to kind of remember these scenarios. And that's why I've attached movies to them, is to help you remember the way that the story unfolds, that this diagram is trying to tell you, right? So all we have to do is, oh, by the way, this is type 1 and this is type 2. John calls them uniform motion problems. That's not wrong. Because uniform motion means constant speed. And what we're assuming in all of these is that everyone's moving at a constant speed. Excuse me, sorry, I'm yawning. If we were dealing with acceleration and deacceleration within the trip, we'd have to use calculus. And you know what? We don't want to do that right now. That'll come later. So you can create problems that take into account speeding up and slowing down, but we don't have to worry about that. So whenever you see that uniform motion phrase, instead of being creeped out by it, be happy. Just go, oh yeah, that makes my life easier, that these are uniform motion. All right, example 29.1. Napoleon, famous French ruler, walked part of the 60 miles to the site of the battle and rode the rest of the way on a caisson, which is like a little cart behind a horse, I believe. He walked at 3 miles per hour and rode at 9 miles per hour. If the total time of the trip was 8 hours, how long did he walk? All right. Here's the situation. The guy's the ruler. He's a famous military hero, not just like a king who sits on his throne and eats bonbons. So he's going to battle, right? And it's a slight variation on our Titanic scheme. He rides part of the way and then he walks part of the way. Does he ride first? He walks first. Okay, so we're going to call this his distance walking, and this is his distance riding. And we know it's going to add up to a total. Okay, so this is a variation of type 2. So the distance walking plus the distance riding equals the whole total. And then we can change this, the d's out to r times t, just like we did here. So we'll say the rate of walking times the time of walking plus the rate of riding times the time of riding will equal the full trip to the battle. Yay, this is the one we want. Now we can make a list over here of all of these variables and go back to the problem and try to figure them out. Don't try to do it all at the beginning because you'll hurt your head. The first thing to do is read the problem just carefully enough to figure out the picture. Then, once you have the picture figured out, get your base equation ready, make your list, now go back in and read the problem in detail. If you read it in detail first, you will hurt yourself, and I don't want that. Your parents will have to call 911 and explain, it's a brain injury. The paramedics will be like, oh, too much math. Okay, ready? Oh, there's actually 3 problems in this lesson, I lied. Okay, he walked part of the 60 miles to the site of the battle. So the full way to the battle is 60 miles. And he rode the rest of the way. He walked at 3 miles per hour. Rate of walking equals 3. And he rode at 9 miles per hour. Rate of riding, 9. If the total time of the trip was 8 hours, okay, so I'm going to write TW equals T8, just a second, I shouldn't have written that, 8 minus TR, right? Because the two amounts together equal 8. So I could write this as TW plus TR equals 8. And then I rearrange it to get one of the variables by itself. That makes sense? Okay, that's usually the trickiest part for students, is figuring out how to take a statement like that and write an equation, because it feels a little obscure. The total time of the trip was 8 hours. So I know that's true, and then I just push the TR over to the other side to get this. This one I'm going to leave as it is, and you'll see it'll all work out beautifully. How long did he walk? Okay, so we're solving for TW. So let's now use our base equation. I'm going to go down here. And let's start plugging in. And I like to put these in the same order as here so I can just kind of go down the list and fill in. 3. And this we said is 8 minus TR. This is 9. This is just TR. And this is 60. And now we can check and go, oh, look, this is going to work out fine because we've got 2 letters, but they're the same letter. So it's going to be fine. Let's distribute, and then I'll flip to another page. 24 minus 3TR plus 9TR equals 60. All right, this goes to my next page. I'm just recopying it. 24 minus 3TR plus 9TR equals 60. Okay? Now, that's just plugged in and distributed. Now we are ready to solve this little monkey. This, let's subtract the 24s. And at the same time, we'll combine those like terms. This is gone. This is what? 36. And this becomes 6TR equals 36. Divide both sides by 6. Thank you, John. And we get the time that he rode equals 6 hours. All right? That's cool. Now let's see if we answered the question. How long did he walk? Ugh. So we didn't answer the question yet. What do we know about the 2 times? Let me go back to my equations. We know that the 2 times add up to 8. And in fact, the time he walked is 8 minus the time he rode. So it's all set up for me. That answers 6, so I know that my time of walking had to be 2 hours. This can be my whole answer, or just that. John shows both of these, but this is the answer that we're looking for. Yay! Beautiful. Okay, next problem. Edward Longshanks and Queen Eleanor were 54 miles apart at dawn. Okay, so they're apart from each other. Edward began the journey to the meeting place, blah, 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 information. The Queen then set out to meet him. Okay, so I'm just looking at the picture. I do not care. This is like the Titanic bumping the iceberg, right? 2 things start from different places and then they bump in the middle. All right, so this is the distance of Edward Longshanks. And this is the distance of Queen Eleanor. I don't want to write 2 words, so I'm just going to say the distance of Longshanks plus the distance of the Queen equals some total, right? I'm just using Longshanks and Queen because that was too complicated. All right, beautiful. They're meeting in the middle, and now I'm going to substitute in my R's and T's here. So the rate of Longshanks times the time of Longshanks plus the rate of the Queenie plus the time of the Queenie will equal the total distance between them, which is just a tragic. They need to meet. Okay, so now I'm all set. I've got my base equation. I'm going to write my variables. RL, TL, RQ, TQ, and K. I like my equal signs. Now we're going back in to get the information. They were 54 miles apart at dawn. Aha, total distance apart, 54. Edward began the journey to the meeting place at 8 a.m. Okay, there's trouble. There's trouble. What that tells me is that they're not giving us the hours, they're giving us clock times. And as soon as I see clock times, I know, oh, I need one more chart. And remember, this is the way the clock time chart works. We're going to write their starting time and their ending time, and then that will give us the total hours that they traveled. This is, let's see, who are we getting information about first? Longshanksy, and then the Queen. Okay, Edward began the journey to the meeting place at 8 a.m. at 3 miles per hour. Rate of Longshanks is 3. 2 hours later, the Queen set out to meet him. Okay, so she slept in. 2 hours later is 10 a.m. If they met at 4 p.m., how fast did the Queen travel? Okay, so rate of the Queen is what we're trying to find. Sometimes I put a question mark there so I know exactly what it is I'm trying to solve for. All right, so now we have to use these clock times to figure out, excuse me, they got up so early in the morning, you know? It's making me tired. Now we have to figure out how many hours they traveled, if these were the times they started and ended their trips. All right, we count on from 8 a.m. 9, 10, 11, 12. That takes us till noon, and then we have to go to 4 p.m. 1, 2, 3, 4. So that is 8 hours for Longshanks. 4 hours to get till noon, 4 hours to get to 4 p.m. Same thing for Queenie. She goes 2 hours to get till noon, right? 11, 12, and then 1, 2, 3, 4. So she is 6 hours, and that makes sense because she started 2 hours later, they told us, but they end at the same time. Great. So now we've converted our clock times into hours. That we can put over here. The time of Longshanks is 8. The time of Queenie is 6. Fabulous. Now we're ready to set up a super keen base equation that we can then solve. Are you ready? I'm going to write it here first, and then I'll copy it over on the next page. So let's get those buckets ready and start pouring in the numbers. 3 times 8 plus, and I'll just use RQ because I don't have that information, right? Times 6 equals 54. Beautiful. Okay, this gets copied to the next page. I'm going to drop the parentheses and we're going to put the 6 in front so it'll look better. But it's 3 times 8 plus 6 RQ equals 54. And then we can multiply this, right? 24 plus 6 RQ equals 54. Swim our little plain number fishies, right? That's gone. 6 RQ equals 30. Thank you, John. So the rate of the Queenie equals 5, and we can put a unit on it. It's miles per hour. John is usually quite kind to us. If a math teacher wanted to be psycho, he could mix in different units, right? And we would have to convert them. Like he could give us one person's time in hours and another person's in minutes. John does not do that to us. John is kind. And so units, we really don't have to think too much about. We just add them at the end. And that's nice. Okay, are you ready? One more problem. I'm going to start on a fresh page because you know what? I don't want to run out of paper on this one like I have on all the others. Our problems are getting so long now that they, for me at least, because I write big, they fill up the whole page. Okay, at noon, Rocket Man whizzed off toward Rocket Land. I'm sorry, what? 1 hour later, Moonfa whizzed off in the opposite direction at a speed, blah, 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 less than that of Rocket Man. So what we have is a little Jetsons energy here. Example 29.3. We've got some creatures, Rocket Man and Moonfa, okay, are in the middle and they're traveling in opposite directions away from each other. Cool, they're Jack and Rose. Let's just take a minute to think of Jack drowning in the freezing water again. This is Rocket Man, so this is the distance of Rocket Man, and this is the distance of Moonfa, and they end up being a certain distance apart. So once again we see, oh yeah, this is a type 2, right? It's Jack and Rose, I already said that. So we know that the distance of each of them added together is going to equal the total trip. And then I can change this, because we know this is true, the rate of Rocket Man times the time of Rocket Man plus the rate of Moonfa plus the time of Moonfa equals K. Moonfa? It's M-O-O-N-F-A. I kid you not. Okay, there's a lovely base equation that we can use. Let's make our list. And then we'll get into the nitty-gritty details. See if we need a clock time chart. I always just keep my fingers crossed and wait to see what happens when I look for the variables. All right. At noon, Rocket Man whizzed off toward Rocket Land. Well, okay. Looks like we're gonna need it. As soon as I see a clock time and not just this many hours, I know that that's the deal. Rocket Man, Moonfa, start, end, hours. At noon, so I'm gonna write in noon. He whizzed off toward Rocket Land. 1 hour later, Moonfa whizzed off. Okay, so that would be 1 p.m., right? 1 hour after noon. Moonfa whizzed off at a speed of 200 kph less than that of Rocket Man. Okay, so the rate of Moonfa is less than the rate of Rocket Man, and it's 200 less. So to make them equal, I need to subtract 200 from the higher speed. And that told me that Rocket Man was traveling at the higher speed. Aha, okay. So I have to be careful about that. That's tricky. If they were 11,800 miles apart at 5 p.m., so that's our ending time, how fast did each travel? Okay, so we can find the times, can't we? We'll be able to plug those in. Let's do that. From noon to 5 p.m., that's 5 hours. And from 1 p.m. to 5 p.m., that's 4 hours. So the time of Rocket Man is 5. The time of Moonfa is 4. And now we've got as much information as we're going to get. We're supposed to find the rate of the two of them. But we were able to rate one of them in terms of the other, so it's all going to work out just fine. So let's set up our buckety buckets. Hello, Luna. I've got a math cat coming in here. Hello. I have 2 cats. They don't cause a lot of trouble. Grace causes trouble. Here's the thing though. When I'm recording lessons in the daytime, Grace just sleeps. She's sleeping by my feet right now. She's perfectly quiet and content. It's at night when she gets crazy and she starts trying to steal food. She's more up and amped. Luna is now investigating my studio. She's walking all around my stuff set up on the table, sniffing everything. Okay, that's enough pet report. Ready? This, we don't know anything, so we just put the variable in. 5. This one, we have a little equation we can write, even though it doesn't fit in my bucket. It's overflowing. 4 equals 11,800. Okay, so I've plugged in. Now I'm going to need to distribute here. So let's rewrite. I'll have 5 times the rate of Rocket Man plus 4 times the rate of Rocket Man minus 800 equals 11,800. Okay, we can combine like terms here and we can add 800 to both sides. That'll cancel that. I'm going to drop down to here. 9 times the rate of Rocket Man equals 12,600. I added that in my head. All right, we better divide both sides by 9, yeah? And this will be fine. Now I'm going to have to do a little long division over here. 12,600 divided by 9. There's no decimals. 9 into 1 doesn't go. 9 into 12, yep, 1 time. Subtract 3, bring down a 6, 4, and that comes out even. So the rate of Rocket Man equals 1,400, and we're working in kph. And I just get that out of the problem. I don't even look. And then I need the rate of Moonfa. And this tells me to take the rate of the other dude and subtract 200. So this must be so there are my answers. And guess what? We're right. And John says, what did he want us to do? He said, how fast did each travel? So there, we've answered his question. You guys, I really, 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 really encourage you to always go back in a word problem and make sure you've answered the question. It's such a thing, especially as you go higher in mathematics. I don't like to be sneaky about it. I like to be straightforward. But a lot of times on placement tests, SAT, or this test that you have to take to find out what math classes you should be taking at Edmonds College, or some professors really get into it, they ask sneaky questions. So always, when you think you've finished the problem, go back and look at the question and make sure you answered it. The question in this one was, how fast did each travel? So we're good. We figured them both out. But just make sure that you're always looking at the answer, because you know what? Some math teachers are psychos. Just gonna put that out there. Of course not me. You would never call me a psycho. But some teachers will try to trip you up and ask a question that isn't as obvious as you think. There are a few cases where John can be sneaky like that. So that's my advice to you. Always go back and reread the question and make sure that your answer actually answers the question. Okay, guess what? 29 is over. Moonfot and Rocket Man are done with their trip, and so are we. Thank you. Goodbye.